Okay, so for today's lecture, we'll also do breakout rooms today, and I just want to let you know because of that, so you guys have enough time. There will be more, I guess, animations. I'm still going to write on the screen, but there's some portions of it that are more graphics, but don't worry about that. It's all in the notes. And today's lecture about single molecule microscopy and super resolution imaging falls right in my research wheelhouse. So I have slides from previous talks that I'm using. That's why it's more animations. But there will be areas where I'll write through, so hopefully it won't be too fast for you guys and we have enough time for the breakout. I know last week we finished kind of quickly and I had to run through some of the aspects of detectors, so I'm going to go over that again. But before I do that, I was wondering if there's any questions at all from last week's lecture. Okay, so we can. So I do want to make sure that we give adequate time to talking about detectors. So this is from the last lecture with optical microscopy, and some of this is in the problem set. So that's also why I wanted to go over it again. That we ended with how do you characterize or compare detectors? And one of these is the quantum efficiency, which is has to do with how many photons that reach the detector are actually sensed or detected or converted to electrons. And this is typically reported as a percentage here. So you can see this is on a log scale for different types of detectors, gallium, arsenide, the different types of detector materials here. And you can see that these can vary based on the materials or the type of detectors with this log scale versus the wavelength. So typically detectors are designed, of course, to work in our favorite region for optical imaging in the visible range. If you want to extend out to the near IR or UV, you'll probably have to make some special considerations with that. We also mentioned that pixel size is important and that there's the physical size. So on the actual chip, like even in your cell phones and your cameras, the detector chip, there's a physical size to those pixels. And these are typically on the order of 1s to 10s of microns versus the image size. So after the image that's being projected from your sample, after it goes through all the lenses and the magnification and stuff, what's the image? 1 pixel in your image that you're detecting, what is that at your sample? So this should be typically 10s to hundreds of nanometers. It can be larger depending on, it's really dependent on your magnification. Spell. And this is where I tried to sketch this type of figure that has to do with the Nyquist sampling theorem. That you need to be careful with your image size, the pixel size for your images, because what you're trying to resolve, if these red dots are the emitters, if they're on the same pixel, you're just going to detect 1 bright pixel. Or if they're close, 2 pixels, 2 bright pixels. But if you actually want to resolve the separation of these, you need to be sampling at the Nyquist or Shannon sampling theorem, which is that you need to have an interval that's twice the highest frequency of interest in your sample. Well, here the frequency has to do with, it's going to be the spatial frequency of objects that you're trying to resolve. Cameras, you also have to deal with noise and being aware of the noise sources with detectors and cameras, where there's shot noise, which has to do with the probabilities of photons being converted to electrons. There's thermal noise, and this is why many cameras, I'd say about 2 decades. On my tablet's dying, give me a second. Thermal noise, I would say liquid nitrogen would be used to cool detectors for like CCD detectors probably about 20 years ago. You'll still see this for cameras that you might find that are a little bit dated. More common, people use Petlier devices to control the temperature. And you also might see like liquid cooling fans to help keep the thermal noise down. But be aware that liquid cooling or fans, those can also introduce vibrations. Then there's also readout noise and multiplication noise. If you're using an electron multiplying CCD, the fact that you're multiplying, there's some variation in the efficiency of that multiplication. And then readout noise has to do with the electronics. When you're doing a measurement with detectors, you need to know the readout rate or how fast you can have frames be detected, or how fast you can read the intensity of pixels. Bit depth. You guys have taken computer science. This has to do with raising things to the second power, or 2 raised to the n, and determines the range of grayscale values. Can be 1 to n at each pixel. So 2 raised to the n, if you're working with 8-bit, that's 2 raised to the 8th. 16-bit, that will be related again to your dynamic range of your camera. And then finally, the gain. That's very similar when I'm talking about electron multiplying. You take a gain as if you take your signal and you multiply it by some value, whatever that gain value is. So I think the gain, quantum efficiency, those are mentioned in the problem set. So just wanted to give some more time to some of the important parameters when you're looking at detectors. So are there any questions with this? Okay. So now we can move to like the main topic of this lecture, which is focusing on detecting. We're going to start the discussion of single molecule detection. And the big question is like, why do we want to go through the effort of detecting single molecules? So that's one of the goals. We'll address why you want to measure single molecules. There's different ways to do single molecule measurements. We're going to be focusing on fluorescence microscopy. So what aspects, components let us detect single molecules? And then related to this, single molecule detection can let you beat the diffraction limit of light. So we're also going to talk about super resolution imaging. And we'll talk about different super resolution techniques. And if we have time, we'll start to get into some of the other ways that single molecules are detected by electrochemical methods or possibly force, but we'll see how far we get. So starting off with this aspect here of why do we want to detect single molecules? So I have some animations here or figures to help illustrate this. So with a lot of the methods that we've been discussing, a lot of the spectroscopy, UV vis, IR, typical measurement will look something like this, a Gaussian-like peak. And if you took a measurement and you saw this type of peak, you would say, oh, there's a very strong high level of signal here. It looks like pretty Gaussian, so I think there's one type of behavior going on. But in actuality, there may be underlying heterogeneity, and these type of measurements are done, I would say, at molar concentrations, or millimolar, or micromolar. But with that order of magnitude, that's going to be like 10 to some large power molecules at a time. But in actuality, if you take this measurement, there may be underlying populations that are behaving in very similar ways, but are truly different. That you can see here, we have overlapping Gaussian normal distribution patterns of this red, green overlapping. We have a slight tail here that you might overlook if you're only just looking at this bulk measurement. So when you're measuring an ensemble, a large number of molecules at a time, this heterogeneity or variation can be obscured because you're limited in your resolution here. So another way to illustrate this, I have a very simple animation. Like let's say we have two different states that a molecule can be in. And it can be rotating to the right and to the left. And if we look at these individually, we can clearly tell the one on the left is rotating counterclockwise, the one on the right is rotating clockwise. But let's say we increase the number of molecules that we're observing. We put them all in a cuvette to do our measurement. And what we end up having is very difficult to resolve of what's going on here. So in this way, if you want to do a measurement, typically you might have to send a pulse in, try to synchronize this, but it's a challenge to try to get all of these many molecules behaving in the same way. So this is a motivation of why single molecule measurements are used, is that instead of doing measurements of an ensemble or a distribution of behavior, what you're really observing are the individual delta functions that contribute to these populations. So you can see here, I've illustrated that with these little arrows. And as you build up the statistics where you're going to be, depending on the type of measurement you're doing, you might be hundreds of measurements to, I would say, even billions of measurements, individual measurements. You build up these populations, but you can resolve these rare cases here, even this orange population that I've shown here, that you can tell the difference between those. So that's the big driving force of why single molecule spectroscopy is so powerful, that you can isolate and observe individual events or behaviors that contribute to the ensemble. specifically focusing on heterogeneous or rare events that would be obscured in the ensemble. You can determine how or why they are occurring. So today, like I mentioned, we're going to talk about fluorescence, but single molecules can be detected so we're going to talk about fluorescence, but they can also be detected by other optical methods such as absorbance. It's much more challenging, or Raman scattering. Again, very challenging. Fluorescence is a typical optical way. And then we'll also talk about electrochemical methods. This lecture, or maybe next lecture, and then force will be the focus of the Thursday's lecture. So these are the three main methods: fluorescence, electrochemical, and force, to detect single molecules. And then this fluorescence technique can also be used for super resolution imaging, or imaging at tens of nanometers below the diffraction limit. So that's the focus of today. So how can we detect single molecules based on fluorescence? We discussed the components of optical microscopes in the last lecture, and we'll go over what those components are. But the main thing is, first, why fluorescence instead of, like I just mentioned, absorbance, scattering, refraction, those types of diffraction and the like. So the reason that fluorescence is used to detect single molecules is it has a high signal capabilities. So you can get, let's say, 10 to the 5th photons per second that you can detect with fluorescence, that it has a high efficiency. Or we talked about quantum yield compared to Raman, which we said is a very rare type of event, or absorption. You would have that high amount of illumination versus absorption. So this high efficiency, the high quantum yield, where typically you're doing measurements with dyes that have quantum yields of, let's say 0.9 or so, something where 90% of the photons in result in a photon being produced out. So this is a benefit of using fluorescence. And in the history of the field, actually absorption was used first to show single molecule detection, and then fluorescence quickly became the method of choice because of the high signals that can be produced. And since we talked about fluorescence microscopy, the difference with being able to detect single molecule is you use high-end or the best components to get as many photons out as you can, so you can get down to the single molecule level. So to do this, the source that you want to use would be lasers. There's no use of lamps with single molecule detection. Lasers, because they're coherent, you can have high powers. It's a monochromatic. Those are the benefits of using lasers for fluorescence microscopy for single molecule detection. You also have to use very high-end optics. So you have to have high transmission or reflection of the filters or the mirrors you're using. So you'll use like silver-coated mirrors that have like 99% reflection, or the filters that you use have let's say 90% or greater transmission, as opposed to using just like dye-based filters that you might see in lower end microscopes. And then the detectors that are used, if you're doing 1D detection, it would be like an avalanche photodiode or photomultiplier tube. This is more historic. Or for a 2D detector, you're going to be using an electron multiplying CCD, or what they call now scientific CMOSs. This is what the S stands for. Where scientific just means that it's a high-end one that has like 95% quantum efficiency. So these all have the electron multiplying, allows for gain. Same with the avalanche photon detector or the photomultiplying tube, that you have a high gain possible. So the photons that you do detect, you can then increase the amount of electrical signal that you can get out. So you can see 90%, 99%, 95%. These are all trying to use the best of the best, or as close to perfect as what is available now. And I'd say these numbers for the detectors was somewhat a limiting capability when this was being developed in the 90s. The detectors were the problem, and then now 2 decades since then, these high efficiency detectors are pretty routine. So after you put a sample that you'll have fluorophores, and you're going to be using these high efficiency, high quantum yield fluorophores, and you're going to be working at very low concentrations, tens of nanomolar to picomolar concentrations. At a typical image, if you're doing a two-dimensional microscopy, or we'll talk about one-dimensional microscopy, you can see here, these are individual molecules being imaged. You can see the length scale here. And you can achieve this by using, like I just said, low concentrations. So they're spaced apart. And that's one thing. And then the other thing is that if you know it's a single molecule, you'll see specific signatures of photobleaching and photoblinking. And we talked about this back in the fluorescence lecture. So I have 2 examples down here of intensity traces of single molecules over time. So this one on the right here, what is this showing? Out of this photobleaching, photoblinking, what's the one on the right with red showing? You guys want to answer in the chat or unmute yourself. Yeah, so Dishani says photobleaching. So this one's just showing photobleaching. The one on the left, what is that showing out of these options? Photobleaching, photoblinking, or both? Yeah, so Bill's saying that this one's showing both. Yeah. And Catherine says photoblinking and maybe some photobleaching. So to confirm that it's photobleaching, you'd have to keep observing for, I guess, a while. But the fact that this data that whoever put it together, that they cut it off, that's probably indicative of photobleaching that took place. Single molecule fluorescence can also be used for FRET. So if you guys remember FRET, fluorescence resonance energy transfer, where you have some molecule that has a donor and acceptor, and based on their distance, you'll see either emission from the donor or acceptor based on energy transfer. So for single molecule FRET, you can see here, this is a trace for an individual molecule where looking at the fluorescence from the donor and the acceptor. So this is the green and the red. Green is donor, red is acceptor. And the signature for single molecule FRET would be that you see anti-correlation of the donor and acceptor signals. So what this means is you can see when, right here, when the donor intensity drops, you see an increase in the acceptor, and then vice versa. So since the signals in the green and red channels should depend on one another, you know you're detecting a single molecule when you see this anti-correlation, and then they take the ratio of these to get the intensity of the donor, or intensity of the acceptor over the intensity of the donor plus the acceptor, is what this plot is shown down here. But anti-correlation is a signature of single molecule FRET. Photoblinking and photobleaching are the signatures if you just have a single dye. You'll also see that show up in single molecule FRET as well. So getting back a little bit to the instrumentation in fluorescence microscopy for single molecule, you can have single point geometries, or you're going to do one-dimensional detection. And we talked a little bit about confocal microscopy in the past. So in these cartoons here, this tan circle would be like your sample. Let's say it's a cell of interest. And with confocal microscopy, what you have, and is what is illustrated here, is a focal volume that you focus at a single point. And you detect this on a 1D detector like an avalanche photodiode or the like. So you can, for single molecule detection, people typically, they can use a confocal setup, or a more specialized setup would be 2 photons, where you would use a fluorophore with 2 photons detection. Fluorophores have to get to the excited state, they have to absorb 2 photons. So this typically uses redder wavelengths, and the benefit of using 2 photon microscopy is this decreases the size of your focal volume. So you can see that only in the concentrated area where that focal volume is, it reduces some of the fluorescence above and below this area. So this is a somewhat specialized form of confocal microscopy. But a benefit you'll see with confocal setups is that you can scan in Z and get 3D information. So that's the benefit of doing single point confocal single molecule detection. A drawback of this is you have to scan in X and Y. So that limits the speed of images. So that's what the benefit is, to overcome that limitation of getting images or looking at a large field of view. The other way that single molecule imaging is performed is wide field methods, where there's 3 geometries I show here. If you just have light being focused over a large field of view, this is called, just in general, wide field, or more specifically, epifluorescence. So that's one way to do wide field single molecule imaging. The problem is your light isn't very focused. Like, you do get in this one imaging plane, but you see a lot of fluorescence from out of focus species outside this focal point here. So that's the benefit of using total internal reflection fluorescence, or a TIRF. This lets you still view a large area. You can see here a wide field of view, but you're only looking at the interface. And we'll talk a little bit in more detail how TIRF is achieved. You're only looking at about 100 nanometers at the interface, and you reduce out of focus signal. So with wide field epifluorescence and wide field TIRF, you get, the benefit is you get a large field of view in 2D, so you can get a lot of information at once. A drawback is you're limited to 2D, no 3D info. So if you do want three-dimensional information, that's where light sheet microscopy comes into play. And that's this last one shown here, which is somewhat specialized, where you have an objective on the side, focusing light through your sample in a sheet, hence the name. This is going to be somewhat thicker. So again, I'd say about 500 nanometers or so. And then you have another objective on the other side detecting that fluorescence. So these are all, again, wide field methods. You get a large field of view versus single point where you can scan through your sample. You know specifically where you're at, but if you would like to get spatial information, you're somewhat limited with the scanning methods. Here. Okay, so getting into a little bit more detail about TIRF microscopy. The benefit of TIRF is you're limiting excitation to the interface. And you achieve this by using, in the name, total internal reflection. Where you focus your excitation light at your sample at a very high angle that's greater than the critical angle of your sample. So if down here, if this is your objective with an oil that's coming in contact with your glass substrate, and up here is your sample, you can, using Snell's law that you may remember from E&M class or other physics classes, the critical angle where you'll have all the light be reflected back instead of having this refraction right here is going to be defined by the refractive index of your sample versus the refractive index of where the light is coming from, this objective oil or glass substrate. And when total internal reflection occurs, most of the light is reflected back, but based on, if we go to Maxwell's equations, you can't have all the light be reflected back without having problems with the equations there. So what you get is at the sample, there is a small amount of light that enters. And this light decays exponentially from the distance from the interface. So if this is the intensity of our light versus Z, how this decays, the intensity of the light will be, I is based on the incident intensity and then just raised to the distance away you're from and a decay factor here. And this D is typically around hundreds of 100 nanometers or so. It can be less than that too. And again, will depend on this angle that you have. There's different ways that you can achieve TIRF that I've shown here. One is you can use a prism on top of your sample and you bring your excitation on the top and then you collect it below with an objective. So the prism method, the benefits are it's cheaper. The drawbacks are you restrict access to your sample. Since you have to have the objective to collect the light and the prism on top, that means both sides of your sample have optics on them. So if you want to have like a flow cell, that's going to be challenging. If you want to be changing things with your sample, it's going to be difficult. But the prism method is relatively inexpensive. There are fancy ways that you can also have a prism and an objective on the same side, but it's quite complicated setups, not very common. The most common way would be using an objective, where if you pass light through the edge of your objective, thinking about how lenses focus light, if it's at the edge, the light passing through the edge, the lenses are going to focus at a high angle. So this is shown in more detail here, where if you have this at the edge of the objective, you can focus a light greater than that critical angle shown here. So this is a more common method. So I'd say this is easier. It still allows access to the sample surface. But cost-wise, this is going to be $12,000 or so objective. So this requires a numerical aperture of 1.4 or higher. So these are very expensive, fancy objectives, and that's why some people choose to use the prism method instead with that. Okay, so any questions with confocal setups, TIRF setups that are used for single molecule detection? Okay, so take a look at this slide. Snell's law is going to come into play. Here, hopefully you guys have written that down. That for the breakout groups, I have different situations, and I'd like you guys to calculate what the TIRF angle would be, the critical angle would be, and why you would want to use total internal reflection over using confocal or epifluorescence. Because remember, I've sketched here, if you use epifluorescence, you're going to have a lot of out of focus light from your sample. So things that would contribute to your background, would contribute to your noise, that would increase or would decrease your signal to background ratio or signal to noise ratio. And similar to confocal, you'll only be limited to 1 point or so. So these are the two questions I'd like your groups to discuss. Let me try to see if I can do the breakout rooms. Take a screen grab of this if you guys would like really quick before I stop sharing the screen. And let me find the breakout groups.
John.
Someone
Hi, John.
comment? So let me share. Okay, well, since, oh, come on. Since we had some overlap with some of the groups, I'd like to hear from both of them. So for groups 1 and 2, if someone from each of those groups can answer, which angle of excitation did you guys get for being able to achieve TIRF?
So for our group, well, we kind of decided, first we need to find the different refraction, like, so for the PLL, we had 1.51, and for the fused silica glass, assuming this is what we're using, we had 1.45, and we got an angle of 73.79 degrees.
And what about the other group?
So we did it a little bit differently. We kind of assumed an aqueous medium instead of the polylysine. So we used indices of refraction for water and the glass. And our glass indices of refraction was closer to 1.5. And the water was 1.33. And so we got an angle of about 62 degrees.
Okay. So both you guys are close. You guys got the refractive index for the glass, and I would assume, and the polylysine is similar to the glass substrate. So it'd be very difficult to achieve an angle with 1.55 and 1.51. And then using water is close, but since these are membrane proteins, I guess I should have made it a little more clear that like since they're in a membrane, that I was thinking more in a cell, or even with a membrane there, that the refractive index is a little bit higher than water. Something like 1.37 in a cell, the cytosol can range a little bit, but 1.37 is a good approximation, but also water is pretty good. So it'd be about 67 degrees or higher than that. And then what about, yeah, I apologize for not listing like it's in a cell with this one. And then what did you guys come up with for the benefits of using TIRF?
So what we found that TIRF is really good for visualizing membrane process, and this is what's happening in here. There's like a cell adhesion to surfaces.
Mm-hmm.
So that's why you don't want to go deep into the imaging what's beyond that 100 to 200 nanometer deep. So we found that this would be the best way to actually, better than the other. And by that also, you're not getting like, for example, the outside signal from the whatever is happening beyond that surface. So you're kind of like getting rid of noise in a way and imaging exactly what you're interested in. Why not confocal? Sorry, I don't know, we didn't answer. We just kind of covered the wide field comparison, but we didn't get to the confocal.
Okay, and then what about the other group? What do you guys come up with?
So, well, we were thinking for the confocal, since this is a diffusion process, that the slower image capture would be less effective.
Yeah, it would depend on, with confocal, it would depend on how fast it's diffusing, and diffusion in a cell memory is slower than, it might be difficult to image multiple processes. So I would say confocal would be a little more challenging to get enough statistics compared to a wide field image where you can collect a lot of information at once. And Rose and her group had a good point of you're not going to see like autofluorescence if this is in a cellular environment from the cytosol. And membranes are typically studied by TIRF since it is a very interfacial process. That's pretty good. Okay, let's move on to groups 3 and 4 then. If you guys have some representatives to talk about what angle you got and what the benefit would be.
We're group 4. We, for the angle, we used the indices of refraction of glass and of water for the buffer of 1.52 and 1.33. So that gave us an angle of incidence of like about 61 degrees. So anything greater than that. Yeah.
Okay. And the other group?
We got above like 59 degrees, so pretty close. We also used fake water and glass.
Yeah, and depending on how many sig figs you include in there or what specific glass and you're using, but yeah, it's pretty close. Okay. And then the benefits of using TIRF?
So I guess we had something similar for confocal. If you're like flowing the buffer over the substrate, and you're going to see like a lot of fluorescent, like if you're trying to colocalize the position of the stationary red dye versus the mobile green dyes, you probably don't want to use some scanning microscopy because it's just not really meant for like, I don't know how quickly it would be moving, but I feel like it wouldn't be very effective in capturing that kind of motion. And then for epifluorescence, if you're flowing the green fluorescent molecule in a buffer over the substrate, you're going to see so much background fluorescence. You probably just get, like all the other data will probably just be drowned out.
Any other comments from the other group?
No, that's pretty much what we said as well.
Yeah. And I would say if you're doing confocal, let's say you're trying to look at the target come into the aptamer, you're sitting on that aptamer and waiting for confocal, you can just look at one at a time. So since you're just sitting there, you might sit there long enough that then the aptamer might bleach and you won't see actually something come in and bind within that time. So again, looking at a wide field, you can get a lot of statistics there quickly. And then finally, let's move on to group 5.
Yeah, so I guess for the angle, we got 40.8 degrees using the refractive index of air, which we just assumed to be 1.00, and glass, which we so I did a quick Google search, and I think it was like Thomas Scientific or some website said that their like 96 well plate had like a refractive index comparable to glass, so we just used 1.53, and then we just got the angle of 40.8 degrees. If benefits of using TIRF, part of our reasoning was that as you said, like TIRF has like less like out of focus light. And Julia, did you want to talk about like resolution? Or?
Sure. I mean, the only thing with resolution is that TIRF has the ability to resolve nanometer length scales, which we would need for this, whereas confocal and epifluorescent wide field can typically only resolve micron length scales.
Yeah, so confocal and epifluorescence, you can still get nanoscales in X and Y. And this was probably the most challenging one, because here, if you're measuring in air, there's not going to be anything that's like diffusing over the top that should be fluorescent. So there's not as much of a benefit if you're doing air. It even took me some time to come up with like a situation where you'd be measuring in air, because I would say in biophysics, there's always some water present there. But you can still get to the same length scale in X and Y, but not typically in Z. But yeah, you guys did pretty good with that. Mostly identifying like what the refractive indices are for what your sample is. Okay. So now we're going to shift gears into super resolution imaging, which is an application of single molecule techniques. At the start, I was talking about like motivations of looking at heterogeneity, but you can also, if you can detect single molecules, you can beat the diffraction limit of light. And the diffraction limit we defined in the last lecture, and it's long been known since the 1870s when Ernst Abbe defined this as best that you can resolve with ideal optics would be your wavelength divided by 2 times the numerical aperture of your objective. So with visible light, if you're using green light, that's going to be around 250 nanometers. So what that means is if you have 2 single molecules, a single molecule here, a single fluorophore, a single green fluorescent protein or the like, you'll see the emission as this diffraction limited pattern, which is an airy disk, which I've described here, that the intensity of a single molecule will be this blurred out spot. And once they become closer to one another and start to overlap within this diffraction limit, it becomes a challenge to localize that. And you can think about when you're doing fluorescence microscopy in a cell that you have dyes all over like a microtubule you're looking at, or the Golgi or the membrane, and this becomes a problem. You get a blurry image at this hundreds of nanometers resolution. But with it, the trick to overcome this diffraction limit uses the concept of single molecules. That while the airy disk is defined by this width of 250 nanometers or so in the diffraction limit, we have higher certainty of where the center of that pattern is, or where the peak is. In the same way that we can describe a mountain not just by its entire base area, but at the exact summit, we can do the same thing when we're looking at individual molecules. So the trick of super resolution imaging is that instead of having this emission be overlapping and having all of your fluorophores on at a time, you'd like to have only one molecule on at a time. If only one molecule is on at a time, you can then find where the center location is and map it. And then if you have these switch on and off, you can repeat this over and over again to then build up an image of these center locations as opposed to the entire emission pattern. So when you perform this localization, you can then, like this is an example here of a cartoon of microtubules where you have a subset of fluorophores on at a time. That's what the glowing orange circle looks like. And then you localize those with the crosses. And this is like frame 1, frame 2, frame 3, frame 4. And when you repeat this over and over again, you can beat that diffraction limit of light. And with this type of localization trick, you can get down to tens of nanometers instead of hundreds of nanometers. If you think back to problem set 1, where you guys were looking at different organelles and different suborganelle organization. This is at the length scale of what's taking place in the cell. This would be too large. So that's the benefit of super resolution imaging, and that's why it also won the 2014 Nobel Prize in chemistry, because of how it's been applied to cellular imaging. There's different ways to achieve super resolution. With what I described on the previous slide, you can have stochastic methods where you're having, when I say stochastic, I'm saying stochastic, that's how you're having the switching or the turn on and off. And these have a bunch of different acronyms, and there's a whole alphabet soup of different names. Some that are most frequently used are STORM, which is stochastic, optical, reconstruction, microscopy. Or you'll also hear PALM, which is photoactivatable, localization, microscopy. And what these use, STORM uses organic dyes. PALM uses fluorescent proteins. And these dyes or proteins have specific wavelengths that if you use UV light, it'll turn on a subset or a specific wavelength of light, and then you can use a redder light to turn it off. So this is using photo switching. These were both developed pretty much simultaneously in 2006. STORM at Harvard from Zhaowei Zhang, PALM at Genoa Laboratories out for the NIH. Another technique is paint, which is points, accumulation, for imaging, nanoscale topography. And this uses adsorption and desorption of fluorophores. Instead of using photo switching, you're having things come in and diffuse and bind and leave. So here's some example images of microtubules where this is your diffraction limited image versus a STORM image where all these microtubules had organic dyes that they could use laser light to turn on and off. While here paint is used, most commonly you'll see DNA paint, where you use complementary strands of DNA, where you can see there's a target that's decorated with DNA, and then you have fluorescently labeled DNA that will come absorb and desorb, and you can build up images where this is used with DNA origami. So that's the most common application that you'll see with paint. So these are using switching on and off, but there are super resolution imaging methods that use hardware instead of samples. So the most common one you'll see is called stimulated emission depletion microscopy, or STED. And this uses, you can see that there's two lasers coming in here. These are two lasers where this redder laser is passed through a phase mask that can control the pattern of the laser. So you have this greener laser is for excitation. The red laser is shaped, so it's a donut shape. And this donut shape is overlapped with the green excitation laser. And this is used to deplete or put the molecules into a dark state. So, dark state. So this is used in basically a confocal setup where you're effectively creating a smaller excitation volume. So this was theoretically conceived in 1994. In 1999, it was actually built, and I wouldn't say until like the late 2010s, this became commercial. Instead, it's more challenging. You can see that with this depletion laser and trying to overlap this donut pattern with your excitation laser to hundreds of nanometers, this is a challenge. So this is less frequently used than I would say. It took more time to catch on compared to Storm and Palm and the like. But I would say that you'll see it more common now that Nikon or Leica, systems that are already built and well aligned, this is becoming more increasingly used. And you can see here an example again of microtubules of a wide field image versus that STED image. Another hardware method is NSOM, or near field scanning optical microscopy. Where near field, when we say near field, that's going to be less than the wavelength of light that you're using. That's what we mean by near field, versus wide or far field would be that wavelength or larger. And with this technique, you break the diffraction limit of light by bringing your light very close to your sample, and you can only collect with this aperture here. This is going to define your resolution. So this is tens of nanometers, where you can only excite and collect. Here in this example, you're exciting your light in the near field based on this tip. So you have a tip with an aluminum coating. Your excitation light is passing through here through this optics, and you're limiting your focal volume there to the near field. You scan it over your sample. This was developed in 1993 and by Eric Betzig. And I would say this is not used as common because it takes a lot of time. It's based on scanning. And again, similar to the benefits of confocal versus wide field, both of these techniques use hardware to then work in a scanning geometry here. So it has some of the examples. There's other techniques. I won't go into a whole bunch of detail here. The expert in our class is Andrew Mayton, who's working on expansion microscopy. And this is a technique that you'll see with tissues, where they'll take, let's say we want to do super resolution imaging on some form of tissue. We can fix it in a dried hydrogel and then introduce that with water, and this expands out. So here, this is what the native sample would look like, where we have these fluorophores overlapping, but this is a physical separation. By literally expanding our sample, moving those fluorophores apart, you can then resolve them and then back calculate what the image is. So this is an example of like a mouse brain slice, where here you can see this is diffraction limited, while this is expanded sample. And in this inset here, you can see the overlap of, or you can resolve the separation from different areas in hippocampus versus here they would be overlapping. But there's always new methods and tons of acronyms with single molecule and super resolution imaging, so be aware of that. So we'll go over the electronic stuff. For the next lecture, we didn't get to that, but if you need some other resources, I have a book chapter, just plugging that, going over the different geometries, TIRF versus confocal, why single molecules, and then some of the chapters that are uploaded on Canvas. So with that, are there any questions about single molecule super resolution imaging? Okay.